this video, I'm going to work out the answers to the first worksheet that was given for chapter 2. The first question is asking to calculate the formal charge of all the atoms except hydrogen in this given molecules. So we will use the formula. Formal charge equals to valence electrons minus 1/2 the number of bonding electrons minus lone pair of electrons. Okay, so maybe it's a good idea for us to redraw the molecule with all the bonds showing. That way we can calculate the number of electrons for the bonding pairs more clearly. So this carbon is bonded to 3 hydrogens. Okay, let's color these carbons because there are 2 of them. So let's put this as red and this one as blue, and then we have the nitrogen and the oxygen. So to calculate the carbon that's red, the number of valence electron is 4 minus 1/2. The number of bonding would be 2, 4, 6, 8. So times 8 minus any lone pairs on this red carbon? No, so we put a 0. And so that would be 4 minus 4, which is equal to 0. So the formal charge in this carbon atom is 0. Now for the blue carbon, it would be again 4 valence electrons minus 1/2, 2, 4, 6, 8 bonding electrons minus 0 again, and that would come out to be 0. So the formal charge in this one is also 0. Now with the nitrogen, valence electrons for nitrogen is 5 minus 1/2. The number of bonding is 8. You count 2, 4, 6, and 8. And any lone pairs? No, so put a 0. So it's 5 minus 4, which is 1, plus 1. So this nitrogen has a formal charge of plus 1. And finally, for the oxygen, 6 valence electrons minus 1/2. How many bonding? Just 2. And how many lone pairs? 2, 4, 6. So minus 6. So we have 6 minus 7, which is negative. So this oxygen here has a negative 1 formal charge. Now similarly, if you calculate the other molecule, the carbon, the first carbon, let's again color that as red. The red carbon will come out to be 0, just like the previous one, because the bonding is exactly the same. Then we have the nitrogen, which also has 4 bonding, and it is in a similar scenario as the previous one. So that will come out to be plus 1. And in the third one, the third carbon atom, which we can color as green, this carbon atom has how many valence electrons? Look at that, 4, right? 4 minus 1/2, and we have 2, 4, 6 electrons. Okay, 6 electrons, and any lone pairs? Yes, 2, right? So it's 4 minus 5, which is equals to negative 1. So this carbon here has a negative 1 charge, the nitrogen has a positive 1, and this carbon has a 0 charge. Okay, so that's how you calculate the formal charges. Moving on to the next question. Here it's asking, using the delta plus delta minus convention, how can you indicate the polarity for each of the bonds that are shown? So we are only concerned about the carbon-bromine bond, and remember bromine is more electronegative than carbon, and the polarity, the dipole's moment sign, is always shown from a positive to the negative end. So in this case it will be this way. Here it is from nitrogen to the carbon. So the carbon to the nitrogen is positive to the negative, so carbon to the nitrogen. And here carbon is more electronegative than lithium, so it's going this way. Okay, it's always from the less electronegative to the more electronegative, and here again it's from hydrogen to nitrogen. So that's how you have to draw the delta plus or delta minus convention. So we have like first we have to indicate those delta plus and delta minus. So it will be the positive end here is carbon, bromine is delta minus, here carbon again delta plus, nitrogen delta minus, here lithium is delta plus, and carbon is delta minus, here hydrogen is delta plus, and nitrogen is delta minus. Okay, next one, it's asking you to draw three-dimensional drawings of the following molecules and predict whether each has a dipole moment. So you can start with carbon. Okay, so if you look at the way carbon is bonded, there's a double bond here, hydrogen, hydrogen. It's a planar structure. Okay, it's a trigonal planar structure with bond angle of 120 degrees. And since it's a symmetrical molecule, here the dipole moment, which is denoted by mu, okay, so dipole moment equals to 0. Now in case of CHCl3, which is another molecule, its common name is chloroform. If I draw the three-dimensional picture, you have to draw it in a tetrahedral form. So there is one hydrogen, one chlorine, and then one chlorine is coming out of the plane, and then one chlorine going behind. So this is a tetrahedral structure. And here, if you draw the dipole moment directions, always goes from positive to negative, and positive to negative. So overall, the dipole moment for this molecule is 0. The next molecule is CH2Cl2. This also, if you draw it in a three-dimensional picture, it is a tetrahedral molecule. Okay, so you make sure that you draw out the correct structure before predicting the dipole moment. So here one hydrogen bond is going back, one is coming out of the plane, then two are in the plane. So again, if you look here, this should be chlorines. Okay, this should be chlorines. Right. So if you look here, we have the dipole acting in this direction. We do not consider carbon hydrogen as a polar bond, so you don't have to show direction of the dipole in this. Same thing in this chloroform molecule, you do not have to show the dipole in this. However, the carbon-chlorine bond is polar and you have to show the direction of polarity. And here again, if you look, I made a mistake here. The dipole moment is not equal to 0 in chloroform, but it should be some value. So we can just say that dipole moment is not equal to 0. And same thing here, the dipole moment is not equal to 0. So you have the overall dipole moment in this direction. For this one also, the overall dipole moment is somewhere in this direction. And this one is a symmetrical molecule with no polar covalent bonds, and therefore the dipole moment is 0. Now the next one is regarding drawing the resonance structure. Here we have a few molecules where charges are given. Some molecules have charges, some do not. So the first one is, we can redraw the molecule here so that we have a better idea of that. So we have a double bond oxygen. I like to keep the lone pair of electrons to give a clearer picture. Also the pair of electrons, wherever a negative charge, it means a pair of electrons. So the first structure you will draw is where you will move the pair of electrons over here and this over here, resulting in a resonance structure which can be separated by a double-headed arrow. And draw this single bond to oxygen, negative charge over here, and then you get the double bond here. Okay, so you have to make sure that you identify the 3 atoms on which the resonance is happening, or the delocalization of the electrons are happening. I have highlighted the 3 atoms. One is the oxygen atom and the other 2 carbons on which the delocalization of the electrons will happen. So that was number 1. Let's do number 2. It's similar with a negative charge. It's a cyclic molecule with a double bond to oxygen. And then here again, maybe you should put out the negative charge with a pair of electrons, and same thing with the lone pairs on oxygen. Now here, if you identify the 3 atoms on which the resonance is happening, it's these 3 atoms again. So you can go ahead and redraw the movement of electrons by putting arrows over here, this peaks over here. So you have a resultant structure, the resonance structure, where you have single bond to oxygen, and then a new double bond is formed over here. Number 3, third structure, is actually has more than one resonance structure. Okay, so you can go ahead and draw the original structure first. Okay, here and here we have a negative charge. Make sure putting the lone pairs on oxygen. Okay, you can actually move this pair of electrons over here and put the electrons in this side. The first resonance structure, where you have a single bond to one of the oxygen atom, the negative charge, double bond to this carbon-carbon bond, and then a double bond to this one. We didn't touch this oxygen, so that remains intact. But actually you can draw one more resonance structure where you can move this pair of electrons back to the to this bond originally, then move this one over here and move this one. So we have 3 arrows here where you can get back the double bond to the first oxygen, and then you move the pair of electrons here, right? And then you have the so we have 1, 2, 3, and then single bond to the oxygen atom. Okay, and the negative charge. So that is the 3 different structures for the third molecule. Now for the fourth one, we'll just go ahead and draw this here. Now you understand that here would be a pair of electrons, right? So the way we can move it is pair of electrons over here and move the pair of electrons at the end. That gives you this structure here where you have a double bond of this, and the carbon atom gets a negative charge. For benzene molecule, the movement of electrons can be shown with arrows in this manner, and you get the resonance structure where you have these pi bonds among these carbon atoms. Okay, hopefully that's clear for the next fourth question. And here this is a little more easier question because you are given the arrows, so you just have to follow the arrows and redraw the resultant resonance structure. So here we have CH3, and you can see that this is asking us to make a double bond. So we have a double bond to this one, and then this is a single bond to this oxygen with a negative charge. This second structure, if you follow the arrow, the pair of electrons are moving over here, and then the other pair is here. So you get the second resonance structure. Third one, again same thing, follow the arrows, you get a double bond to oxygen, the lone pairs here, and then we have this structure. We have the pair of electrons at this carbon atom. Just follow the arrows in this one, okay? And you get the resultant structure. Always remember, if you start your molecule with a charge, your end molecule should, or the resultant resonance molecule should also have a charge in it. Okay, so some things to remember to take care are charges, and make sure that the octets of the atoms are also complete. This question is asking you to draw the resonance form of carbon dioxide. So first we draw the normal, more common form of carbon dioxide structure, which is a linear structure with a pair of electrons. And the one way we can draw the resonance structure would be to move this one pair of electrons over here, right? But simultaneously you move the other pair to the oxygen atom. Okay, so we will have a resultant structure where you have a single bond to the oxygen and the carbon oxygen single bond, and then we have actually a triple bond to this oxygen with one pair of electrons. Okay, so and that this will give us a negative charge over here, and this oxygen will have a positive charge. Okay, so these are the two resonance structures that are possible. This is the more common one that we always draw. This is the less common one, and it's asking which one would be the major contributor. And we had discussed this in class, that the major contributor would be the one which has minimum formal charges, which is structure 1. So this would be my major contributor. The one that has got formal charges will be my minor contributor. Okay, the next question is, actually this should have been written as which of the following will have the strongest conjugate base. So I'll rewrite this again. Okay, which of the following acids will have the strongest conjugate base. That should have been the question. I apologize for the error in there. Okay, so now the rule is that lower the pKa, stronger is the acid. Okay, so that's one rule. And the second is that a strong acid will always have a weak conjugate base. Okay, so first let's predict which is the strongest acid, the one which has the lowest pKa. So water has the lowest pKa among the three here. So this should be my strongest acid, and this should therefore have the weakest conjugate base. And then this methane will be the weakest acid because its pKa is highest, weakest acid, and that will have the strongest conjugate base. So to answer the question, it should be this one that will have the methane will have the strongest conjugate base. Then which of the following base is strong enough to deprotonate? So here the best way to answer is draw out the corresponding acids of this. So these are the conjugate bases of the acid, and it's asking that if you react it with acetic acid, each one of them, this is acetic acid, whose pKa is 4.8. Say for example you treat this with the first one, okay, which is a carbon with a negative charge. Here there is a carbon with a hydrogen, alright, and the product would that be CH3COO minus, where the base has removed the proton, the electrons here, so we get a oxygen with a negative charge, and HC triple bond CH. Okay, that will be my product, and the pKa of this acid is what is given, that's 25. So here we are starting from a stronger acid going to a weaker acid. Yes, this reaction would work because the equilibrium always goes from strong to weak. So this is a equilibrium which is favorable in the forward direction. Okay? It always goes from strong acid to weak acid. So this base will be able to deprotonate this acid. What about the next one? Same thing here. We have CH3COOH plus H minus, H hydride. Same thing, you can remove the proton, put the electrons here. You have CH3COO minus as the conjugate base of that acid, and hydrogen. Now hydrogen's pKa is 35. This is given as 4.8. Again, as per the previous rule, the equilibrium will definitely move in the forward direction because we are going from a strong acid to a weaker acid. So check out this one too. Now let's check the third one, right? I'll write it down in the next page here. Same here, we have a CH3COOH reacting with chloride Cl minus, and then show the arrow moment or the electron moment through arrows, and here we have CH3OO minus, and the product is HCl. That's the acid for this conjugate base. The pK of this acid is -7. Now this is 4.8. So which one is stronger? HCl is a stronger acid, right? This is my stronger acid among the two. So equilibrium will be pushed actually in this direction. Okay, it's favorable in this backward direction, not in the forward. So this reaction will not happen. So to answer the question here, the bases which are strong enough to deprotonate CH3COOH, which is vinegar, is this one and this one, the chloride. Now moving on to the next question, which of the following, oh, this actually was an error here. We don't have a question to it. As for that, okay, so there is no reaction here, so we can skip that. This is actually question number 9, where it's asking you to identify the most acidic proton and explain your choice. So here the most acidic proton is actually the hydrogen, which is labeled as HA. HA is the most acidic proton. The reason is that if you remove HA, you can actually draw resonance structures for this molecule. Okay? So the conjugate base, so you can say that the conjugate base will be stabilized by resonance structures, And what I mean by that is that if you take this molecule, okay, and remove that proton that is attached to this oxygen, what is remaining is my conjugate base. Okay? So this is the conjugate base of this molecule where you remove the proton from it. So this oxygen gets a negative charge. So this conjugate base can actually be stabilized by resonance in this form. So that electron pair can be delocalized over the two oxygen atoms, which is a phenomena of stability. So that's why this proton is the most stable one. If you remove this proton B, which is labeled as P, you can get a negative charge here, and maybe you can do resonance on the benzene ring, but the problem is you will get a positive charge on the oxygen atom and a negative charge on the carbon atom. There will be a negative charge on the carbon atom rather than on the oxygen atom. Whereas here in both the resonance structures, you can see that the negative charge is being carried by the oxygen atom. Okay, so that's why this one, the preferred proton to be removed in an acid-base reaction, is the one that is labeled as HA. Okay? And the other carbon atom, hydrogen atoms which are labeled as HC are not acidic enough because they are connected to carbon atoms, right? And so the ones that are connected to oxygens are the ones that are more easy to be given off in an acid-base reaction. So A and B are acidic, but among them, A is more acidic than B because the resonance structure of the conjugate base produced by removal of HA is stabilized by resonance, where the negative charge is carried by the electronegative elements, which are oxygen atoms. Okay, that's how the answer should be, complete answer. Next question is asking for the following compounds arranged in increasing order of acidity. So here CH3COOH is more acidic than CH3, CH2OH. Reason being that the conjugate base of CH3COOH is stabilized by resonance. That's the reason. In this question, to get full points, you should actually draw out the resonance structure like this. So we have the CH3COOH. After the proton is removed, you get the conjugate base like this. You can show the movement of electrons by these curved arrows, and you get the single bond to this oxygen atom. double bond to this oxygen atom now, which is a case of stability. Whereas in case of CH3CH2OH, which is this compound, you can see that the conjugate base is this one, but no resonance stabilization. So the one which has got more resonance stabilization is the one that will be more stable. In case of the second question, the trend would be based on inductive effect. The one which shows the greatest inductive effect will be the strongest acid. So it's increasing acidity. So we will say that, when they say increasing acidity, the lower one should be written first, right? So the least acidic would be CH3COOH, which will be less acidic than Cl3COOH, which will be less acidic than CF3OOH. So this is based on inductive effect. The greater the electronegativity of the element, like fluorine, it will show more stronger inductive effect, as a result of which the highlighted proton, which is the proton we are talking about, this one. In each case, this is the proton that will be removed, and this proton is easy to be removed in this case where the electronegativity of the atom is highest. The next question is actually based on elemental effect. So the proton is connected to nitrogen here. Here protons are connected to carbon. Here proton is connected to fluorine, and here it is to oxygen. So the most electronegative is fluorine. So HF will be the most acidic, and CH4 will be the least. So the trend would be CH4 less acidic than NH3, less acidic than water, which is less acidic than HF. This is the trend, and it is based on elemental effect, or to what element the atom or the proton is connected to. Last two questions. This 11th question is based on Lewis acid, Lewis base. Now remember the definition of Lewis acid. It is something that can accept electrons. This is based on electrons. Okay, accept electrons, and Lewis base is something that can donate electrons. So something that is rich in electrons will be a Lewis base, and something that is poor in electrons will be a Lewis acid. There's a different name given to these, and something that's poor in electron is called as electrophile. Okay, it would be nice to learn these names now, because we will be talking about this quite a lot in our rest of the discussions. So, and anything that is electron poor, like this Lewis acid, is an electrophile. Anything that is electron rich is called as a nucleophile. Okay. Anyway, that's just an extra information here. So first of all, in this question, you have to identify which one is a Lewis acid and which one is a Lewis base. Now, if you draw out the structure of AlCl3, you can see that it has got 3 simple bonds to 3 chlorine atoms. So that means there are only 6 electrons in its octet. So this is short of electrons. Okay. So AlCl3 should be my Lewis acid, and this guy should be my Lewis base, because now you have chlorine with lone pairs of electrons, so they can actually donate electrons to aluminum, and that's how this reaction should be. Okay. The last question is coming back to the Lowry-Bronsted acid-base theory, where it's asking you to draw curved arrows. So draw the carbon with a pair of electrons, negative charge, to make it a clearer picture. It's reacting with water. You can draw the bonds to water. And finally, your structure is where you have a triple bond, then connected to a hydrogen, and then OH. It's minus, that means you have lone pairs, and that's a negative charge. So to show arrows, remember it's always goes from an electron rich to electron poor. So this is my base. Here is my base. That water is my acid. It's removing the proton, putting the electrons on the oxygen. That's how you should complete the reaction using the curved arrow mechanism. I hope this worksheet is clear, and I'm going to post this to the module related to chapter 2. And if you have any questions,